Hi everyone, this is Miriam Naime from the Alan Turing Institute and Newcastle University. Welcome to our SuperGen Smart Charging webinar series. The webinar is an activity of the Vehicletogrid integration group at the Turing, which is the National Institute in the UK for Data Science and Artificial Intelligence. We have a YouTube playlist for the webinar where we hosted speakers who spoke about communication protocols for electric vehicles and cybersecurity, among other topics. On that note, we just published a white paper on the security of the electric vehicle charging infrastructure, and if it is publicly available, if you want to check it out. On the webinar, we try to cover topics that are relevant for electric vehicles and smart charging. And one of the key topics is battery degradation. So today, I'm delighted to host Matthieu Dubarry, who pioneered the use of new techniques to analyze degradation of lithium-ion cells without destroying them. He also developed numerous software tools to facilitate the prognosis of lithium-ion battery degradation, both at the single cell and at the battery pack level. And Matthieu is currently working on evaluating the impact of V2G strategies on the degradation and also testing emerging battery technologies for both grid-connected storage and transportation. So without further ado, Matthieu, over to you.
Thanks, Miriam. Let me share my screen. Okay, do you all see my slides now?
Yes, we see them.
Okay, so hello everyone. As Miriam mentioned, I want to talk about lithium-ion battery diagnosis and prognosis. And as a subtitle, I want to add that I'm going to show you how to use synthetic data to learn about yourselves. And I think that's really important for the artificial intelligence and big data applications. A little bit more about me. At first, I'm a material scientist. I have a bachelor in technology in material and physical characterization. I have 2 master's degrees, one in material science and one in ceramic engineering. And I did my PhD full-on material science on the synthesis, characterization, and optimization of materials for lithium batteries. I started working on fuel cells when I started working for the Hawai'i Natural Energy Institute in 2005. And since then, now I'm leading my own group for the past about 10 years. And as Miriam mentioned, we do a lot on the battery diagnosis and prognosis. So what we do most is trying to diagnose the cells and prognose them without having to open them or doing anything destructive to them. And so for that, we define a set of performance metrics. We do a lot of design of experiments to understand how the cell degrade under a given condition. And I'll go back to that a little bit later. We also try to develop tools that are going to be valid for lab tests, but also on deployed system. And so for that, we also do online state of charge and state of health monitoring for deployed system. And you have an example here of one of the systems we have for HNEI. It's a big battery, 1 megawatt battery that's on the grid. We also do some modeling, and that's because in the lab, we are testing single cells. And obviously, we want to transfer that knowledge to the full battery pack. And so that was most of our work to develop those methodologies. In recent years, we also starting to work on applying those methods to understand better batteries on the grid, or in vehicle to X, X to vehicle, understand how the battery degrade under different applications. And we're also really interested in second use and in the recycling. We haven't really started that activity yet. Quickly on motivation, we are lucky to be in Hawaii. It's a great place to test different technologies because we're a small islanded grid. And we also have a wide array of climates, a wide array of road conditions for EV. You can go from mountain road to really dense traffic. And we also have some big incentives to develop new technologies because we need to be 100% clean energy and transportation by 2045. So it's really a good place to be to work on renewable energies and batteries. Okay, so Miriam asked me to start with a little bit of the basics, and I wanted to start by the principles of a lithium-ion battery, how it really works. I'm sure you look at in school to make some batteries with a potato and putting 2 coins or a paper clip in a potato and connect it to a light bulb. And yeah, that's a battery and it works. And the way it works is the electron go through the metal electrode, and then when it reaches the interface with the electrolyte, the ion is going to be released and release one electron that's going to go on the other side. But that's a simplified version of a battery. A lithium-ion battery don't work like that at all. A lithium-ion battery rely on intercalation. And what that means is the ion and the electron are not going to plate at the surface of another electrode. They're going to go inside the crystallographic structure. And then they need to move inside the structure to go towards the core of the grain so another ion can come in. So it's much more complex than just plating at the surface or stripping an electrode. As a result, the atoms around the crystallographic structure is going to change to accommodate more and more lithium in. And here I show you an example of vanadium pentoxide. You start with really nice layered structure made of the vanadium pyramids. And when you put lithium in, you can see that the structure change and the pyramids, the organization of the pyramids is more and more distorted until you kind of break the layer and reach a really compact structure. So that's much more complex than a simple plating at the surface. The other side effect of that is that usually those materials, they are insulative. They cannot conduct electrons. And so that means that your electrode, the architecture of the electrode is going to be much more complex than a metallic rod. Usually you have something that looks like that. You have your active material, and then you have those little carbon spheres that are here to make sure you have some electronic conductivity. And then you also need a lot of porosity so that every grain can be weighted by the electrolyte. And the last thing you see is that cheese-like compound here, that's a binder. And that's because when you put lithium in and out of those materials, the volume is going to change a lot. So you need some kind of a binder to ensure you have mechanical integrity and you can charge and discharge your cell thousands of times. Let me show you another example of the impact of intercalation. Is that the voltage of the battery is going to depend on the structure. And when you change the structure, the voltage of the battery is going to change. And usually when you have a phase transformation, the voltage is a constant. I don't have time to go into the thermodynamics behind it today, but think of an analogy with water and ice. When you want to prepare some ice cubes, you put the water in the freezer. And what's going to happen is the temperature of that water is going to go down to 0 degrees Celsius, and then you're going to start to form ice. And the temperature of that mixture is going to stay at 0 until the last drop of water disappears, and then it will go down to the temperature of your freezer. So here we have exactly the same thing. You just replace temperature by voltage. So that's an example of graphite. And graphite is the negative electrode that's used in probably more than 99% of the lithium-ion batteries on the market today. So the structure of graphite is really nice layers of carbon rings. And so when you're going to put lithium in, thermodynamically, the lithium is going to go into the most favorable place. And actually, at first, the lithium is going to go in 1 layer out of 4 of the graphite. And when all those layers are full, then thermodynamically, the next most stable phase, if you want to put more lithium in, is filling 1 layer out of 3. So the structure is going to change from that one to that one. There is nothing intermediate. It's either that structure or that structure. And then when that's full, you're going to start changing structure again and then filling 1 layer out of 2. And then finally filling every layer of the graphite. And that's why you see that response here with all the plateaus, because of all those change of structure. And that may seem complicated, but actually that's really useful for diagnosis and prognosis, because those change of voltage give you information on the thermodynamic state of your battery. And I'll get to that a little bit later in this talk. The other thing that sometimes people don't realize that lithium-ion batteries is actually a family of compounds. And not every battery is equal. Not every battery uses the same active materials. And so Miriam asked me to touch base a little bit on that. So commercially, you have three big family of materials for your positive electrode. You have the lithium cobalt oxide family with lithium cobalt oxide, lithium nickel oxide, and some doped compound like nickel cobalt aluminum oxide or NCA, or lithium nickel manganese cobalt oxides or NMC. You have another family of compound with lithium manganese oxide, and a third family with a lithium iron phosphate. The way they differ and why they separate is by their structure. Those structures, the lithium cobalt oxide family, they're layered material. So you have nice layers and the lithium go in between. And so in a way, the lithium can come in that material from two directions. The lithium can come here from here, and the lithium can come in from here. The LiMn 204 materials, they have a spinel structure, so a different organization of the atoms. And in that structure, the lithium can come in by three directions. Lithium iron phosphates or olivines, they are one-dimensional materials. The lithium can only come into one direction. So it's three different family of compounds, and they have different characteristics in terms of energy, capacity, power, safety, performance, lifespan, cost. So depending on your application, you need to choose the most adaptive materials. So here you have a summary of the performance. If you're interested, I have a link to the paper where I took that figure here, if you want more details on that. But just to show you that lithium-ion battery, most of the time, they're going to work really well for one application and not the other. And also, they're not interchangeable because they might contain different materials that cannot be used the same way. For the negative electrode, that's a little bit more complicated. So here you have all the positive electrode. The negative electrodes are here. 99% of the lithium-ion batteries in the market today use graphite as the negative electrode. The ultimate goal is to be able to use lithium metal or silicon because they have 10 times the capacity of graphite. But there are a lot of problems with using those. Most state-of-the-art batteries now use probably 10% graphite, 10% silicon in graphite. Commercially, you also find batteries with that material here, Li4, Ti5O12, or LTO for short. So as you can see, that material has less capacity than graphite and also a much higher voltage. So that means that those batteries, they're going to be 2-volt batteries instead of 3.7 or 3.8-volt batteries. But the benefit of LTO is that smaller voltage means the electrolyte is more stable. And so those batteries don't degrade much in calendar aging. And I'll show you examples of that later. And the other benefit is that LTO is a single phase material with almost no volume change. So you can put lithium in and out really fast without too much strain and stress. And that means you have a really good durability. So you have some commercial batteries, not a lot, but for storage application or for buses that recharge a lot, that use lithium titanium oxide as a negative electrode. Okay, let's start to go into the meat of the topic of today and the lithium-ion battery diagnosis and prognosis. And starting with diagnosis, it's a really complex task. And that's because the battery degradation is path dependent. And what I mean by that is not just losing capacity faster or slower depending on the condition, is that the internal degradation of the cell is going to be dependent on the way the battery is used. So if you take the example of an electric vehicle, depending on the temperature, depending on your driving habits, on the road type, on the traffic, on the charging habits, and on the grid ties, the degradation might be different. And that will play a big role on the durability of the cell. Depending on how it's used, you might stay on path A where the degradation is linear, or you might be on another path where the battery is going to die at what seems a random point. So it's really important to understand what stress factor can induce those kind of degradation. But also the issue is that every battery is going to be different. There's not going to be two EV today on the market that's going to be used exactly the same way. You cannot compare an EV used in Newcastle to an EV used in Honolulu or in Arizona or in more colder place like Sweden, because they're going to see different conditions, they're going to degrade differently. And so you need to make sure that the tools you have for onboard diagnosis and prognosis are able to understand the change of condition and be able to adapt to the different degradation. And so that's why diagnosis is really complex. And the way I like to represent it is with a balance between the accuracy you want and the resources you're willing to put. In academia, we tend to have a balance shifting in that direction. We can reach amazing accuracy and understanding exactly what happened to a battery. We can do post-mortem, alpha analysis, a lot of modeling. And we have really great tools that are really accurate, but the resources we're willing to put are really high. I mean, sometimes it takes years to analyze just one set of experiments. On the other hand, on deployed system, you want the exact opposite, because you want as little resources as possible. Obviously, if you think of an electric vehicle, you don't want to spend half of the capacity of the battery just for the self-diagnosis. You want to use that capacity for driving. So as a result, you want simple characterizations that are fast and also that are fully automated. But as a result, usually the accuracy is pretty bad because you're just monitoring capacity and resistance. And so you cannot really do any prognosis on your results. So what I'm going to show you today is that the method we developed in the past decade are really balanced, where we can have a really good diagnosis with limited resources. So if you want to talk about battery degradation and diagnosis, you need to understand what could happen to your battery. And if you remember the picture I showed you earlier of a battery electrode, it's really complex. You have your active material, you have your carbon additives, your binder, you need to make sure you still have porosity and so on. And so those electrodes, chemically, they're really complex. Most of the time, also, the electrolyte is not fully stable over the voltage window and so on. And so a lot of different things can happen to your positive or your negative electrode. And here is a list that's non-exhaustive of some of the degradation mechanisms that can happen. And depending on how the cell is used, you might inhibit some or exacerbate some. For example, and don't quote me on that, it's just an example, that one might be really sensible to the current at which you charge and discharge the battery, but that one is not. That one might be really sensible to the temperature, but that one is not, and so on. So that's why every different usage going to lead to a different mix of those degradation, and so to a different diagnosis, and maybe later in life a different prognosis. If you want to do a full diagnosis of your battery, you need to quantify each and every one of those mechanisms, plus all the ones that I haven't put on the slide. And so that's why it's a lot of work and it takes a lot of resources to fully diagnose a battery. And obviously that's completely impractical and impossible to do that on board without destroying the batteries. To access some of those, we need to open the battery, do microscopy or some advanced spectroscopies and so on. And so if you want to have a good diagnosis on board, you cannot really go that deep. What we propose doing is to go one step above and focusing on what we call degradation modes. And what we mean by that is focusing on the impact the degradation is going to get on the cell. And for example, all those degradation here is going to change the amount of active material. And so independently of which one happened, the voltage response of the cell is going to be the same because you lost active material. Some's going to change the amount of lithium inventory. Some's going to change the kinetics of the cell. And obviously some can have, be one of those or two or three. But that's a simplification. Instead of having to quantify 20 plus mechanisms, we just have to quantify 3 degradation modes. So, of course, we need to find a way where we can do that non-intrusively. and using the sensors that are available in the field. If you think about an electric vehicle like a Tesla with 10,000 or so batteries in it, you cannot really ask to add one sensor per cell because that will add a lot of cost. So you need to do and use what you have available: voltage, current, and temperature. And as I showed you earlier, the voltage is really interesting because that voltage for intercalation batteries carries thermodynamic information, because it's going to tell you the structure and which phase the lithium is in. And so if you study the evolution of the voltage response of the battery, you should be able to derive information. The problem is those voltage versus capacity curve, although you see change when the battery age, it's really difficult to quantify those changes and to discuss those changes. If I show you those three curves, it's almost impossible to describe how the voltage response change besides we have less capacity. So what we propose doing, us and others in the mid-2000s, is to start to look at the derivative of a voltage curve. And when you look at the derivative, that's exactly the same data here. You can see that now we can start to discuss and we can start to quantify the changes. For that cell, when the cell aged, so from the black curve to the red curve, that peak went down, that peak went up, that peak went down. Oh, sorry, it's a negative curve. And that peak is shifting. And so that's information. We can visualize how the cell change or the voltage response change based on the degradation. Now, the key is to relate those changes to some particular degradation mode. And that's where it was really complicated, especially for that derivative here. And that's because that complex voltage response, that complex derivative with all the peaks, that's a convolution of the response of the positive and negative electrode. So let me show you what I mean by that. That's the derivative curve of the graphite. If you remember in one of the previous slides, I showed you the voltage response of graphite with those nice plateaus. If you derivate a plateau, you're going to get a Dirac peak, and that's what you see here. So graphite has 5 peaks, 3 are really well marked, and you have 2 small ones here. But you can see that it's pretty hard to see on the full cell response where those graphite peaks are. Now, if I look at the positive, I choose on purpose the most complex case possible because my positive electrode is a blend. Some commercial battery might use 2 or more active materials together, and that's to have some more balanced properties for the cell. So in that example, I have some NMC and some spinel together, which is a classical combo, if I can say, of materials. And I think that's what was used in the first generation of the Nissan Leaf. And so that's the signature of the derivative signature of NMC. Oh, sorry. That's the derivative signature or alignment 204. And so the signature of the positive is going to be the sum of the 2. But again, it's pretty hard to see the link between that curve and that curve. And that's where our contribution happened in the mid-2000s. We were the first one to really decipher the code and understand how we can go from those 2 curves to that one. And the key was to look at the problem as communicating vessels. So let me show you a graphical example on how it works. What you need to do is imagine the derivative curve of your negative electrode like that, and of your positive electrode like that, and align them so they resemble a water clock. So that shape, the derivative curve of the negative, is going to be the shape of the top bulb here. And the derivative curve of the positive here is going to be the shape of the bottom bulb here of the water clock. And imagine the lithium as an incompressible liquid inside that water clock. And so when you start discharging, most of the lithium, most of the liquid is in the negative electrode. And there is a little bit on the positive. So in that analogy, the voltage of my battery is going to be the difference of level between the level of liquid in the 2 bulbs. And if I look at on what reaction I am in each electrode, I'm on reaction 1 on the negative, 1 on the positive. And so that little shoulder here corresponds to that reaction convoluted with that reaction. Now I can flow some lithium from one bulb to the other, and obviously that level is going to go up, that level is going to go down, and so my voltage is going to go down. And I can see if I stop at that random point, that's going to be reaction 2 on the negative and reaction 4 on the positive, and that corresponds to that peak here. So if we do that really carefully and really slowly, we can index all the peaks on that curve, and we can separate the contribution of one side of the blend to the other side of the blend. And so with that, we can start looking deeper into those curves, and we can start to think on what happens if the cell degrade. So you see in the same analogy, now you can start thinking about, okay, if you lose positive electrode, what's going to happen is the bottom bulb is going to become smaller compared to the top bulb. So I go from that configuration to that one. Same voltage for all the peaks, but just a smaller bulb. Since my liquid is incompressible, now for the same amount of liquid at the initial point, the level is going to be higher. And so the voltage of the cell is going to be higher, and it's also going to influence the lithium is going to, the voltage when the lithium is going to go from one bulb to the other. Because that capacity here, instead of going on the shoulder here, now that capacity is going to go inside that peak. And so the voltage response of the cell is going to change. If you lose lithium inventory, that's even easier to understand. You just have a leak. So you have two bulbs that are the same here and here. You just have less lithium in the top bulb for the same level in the bottom bulb. If you change resistance, the distance between the bulb is changing. And if you change your Faradic resistance, but your charge transfer resistance, the voltage response is stretched. So the peaks get broader and broader. And so with that simple analogy and from really careful analysis, you can predict how the voltage is going to change depending on a given degradation. And you can do that without the need for postmortem analysis. Just based on how the voltage change, you can, by using logic, understand how the cell degraded. And so you can establish a diagnosis where you can, from those changes, establish that you lost some lithium, you lost some active material, and you kinetic degraded. And so you can quantify the free degradation mode. Let me show you one real example. So here you have two cells. They're lithium iron phosphate cells, high power cells, and exactly the same cells from the same batch. One, the black one, was cycled by simulating 3-hour drive and then charging the cell in 15 minutes. The blue one was tested by charging and discharging in 15 minutes. So really aggressive usage of the cell. That one is more driving with kind of a fast charge. And you can see that after 600 cycles or so, both cells lost capacity at exactly the same pace. They seem to be, in terms of degradation, they seem to be doing the same thing. And if you look at the spec sheet for those cells, they're supposed to last 2,000, 3,000 or so cycles. So you should be good to go. But actually, if you analyze using our tools, you can predict that the black one, which is the one that was used the least aggressively, is going to die, where the blue one is fine. And when we keep testing, we were absolutely right. And we could make that call because when we look at the derivative response of the cell, we notice that they were the same at first, but at that point and at that point, they did not evolve the same way. And we could use that information to quantify that both cells lost lithium at the same pace, and that's why you have the same loss of capacity. But the black one was actually losing negative electrode eight times faster. So at that point, we could extrapolate those trends and use those extrapolation to recalculate the voltage response. And that's how we were able to predict that that one was going to die, that one is fine. So just to show you how powerful that method is, just based on the voltage response of the cell, we can get diagnoses good enough so that we can extrapolate them to reach prognosis. The problem was doing it by hand required a lot of work. It was really tedious work. You don't imagine how many times I printed a curve and then starting to manually cut some peaks to weight them to see how the area changed and so on. So it was not really convenient for quantification. So what we did in 2012 is put the clepsydra analogy, the water clock analogy, in a simple mechanistic model. In a way, we wanted to build a digital twin for the cell. And we wanted to use a model that did not require too much calculation and that was really simple to use. So we decided to start from half cell data. We can quite simply test the positive and the negative electrode versus metallic lithium. If you have a new commercial cell, is open it in a glove box and harvest each electrode and test it versus metallic lithium. And so you can see how the positive electrode change with rate and how the negative electrode change with rate. And then you can, with simple equivalent circuit models for each electrode to be able to handle different rates, you can match both electrodes so that you replicate the voltage response of the full cell. And so the matching, you just have two parameters, the loading ratio, and that's pretty much the capacity difference between the positive and the negative electrode. In a commercial cells, graphite base, you usually always have a little bit more negative than positive. And that's to limit the risk of lithium plating. So you need to match that difference in capacity. And also you need to change, add an offset between the two electrodes. And that's because, as you probably all know, on the first cycle of a lithium ion battery, you form an SEI layer. You form some passivation layer, and that consumes quite a bit of capacity. And that's what you see here. That's what makes that offset. But you can see that based on that experimental information and just matching two parameters, we can match the voltage response of the commercial cells. And here again, I'm showing the derivative just because it enhances all the changes. So here we're matching really well all the peaks and their shape. And that means that we're matching all the electrochemical reaction in the cell. And once we have that digital twin, all we have to do is change the matching to emulate the impact of the change of active material, change of lithium inventory, and change in ohmic and faradic resistance. In a way, we just put that clepsydra in equation here. And that's how we can emulate all those different degradation. And so now what we can do is fit the initial response of the cell to get the initial parameters, fit the degraded cell. And here you have an example of beginning of life in blue and end of life in black. And that shows you how well we can replicate all the different changes. And from there, we have a diagnosis. We can know, by knowing all the loading ratio and the offset change, we can calculate with a simple set of equations how much lithium we lost, how much positive we lost, how much negative we lost. And here you have an example of a diagnosis we can reach for a calendar aging study where we add a blended positive electrode and a negative electrode. And you can see that in that example, depending on temperature and state of charge, depending on the material, the degradation was not the same. And for example, in that case, the lithium cobalt oxide was a little bit sensitive to temperature, but quite insensitive to state of charge. Whereas the loss of negative electrode has a big combined effect. On its own, temperature don't have a big effect, or SOC don't have a big effect, but the two together has a really strong effect on the degradation. And that's an example of the path dependence of the degradation I mentioned earlier. Depending on the condition, you might inhibit or exacerbate certain component of the degradation. And so for prognosis, what we can do, as I showed you earlier, is do a diagnosis several times and then extrapolate those trends to be able to recalculate the voltage response of the cell. And that's how we can predict if the cell is going to enter a second stage or not. So it's a really powerful tool to diagnose and prognose the battery degradation. So if you're interested, we actually put everything into a simple graphical user interface, and we're licensing it for free for academic use. And if you're industrial, contact us and we can discuss the licensing fee. But it's a really powerful tool to show you how the voltage response change depending on a given degradation. So in our tool, we can switch change chemistry as much as we want, and we can simulate any evolution of the loss of lithium or the loss of positive. And actually, our tool right now, we have more than 100 users from more than 50 organizations worldwide. A lot of national lab in, sorry, a lot of national lab in the US, a lot of prestigious universities all over the world, some battery manufacturer, and even some electronic assemblers are or were using our tool to understand their batteries better. So if you're interested, please do not hesitate to contact me. Okay, moving on to the next part of my talk. What I showed you so far was only on the single cell level. Obviously, for deployed system, whether it's on the grid or on the road, we're going to need to deal with battery packs. And that adds a lot of complexity. And here's an example, and that was for a Tesla, but it's kind of true for all the vehicles out there. There have been some instances where some vehicles that were towards end of life stopped on the road because the battery was drained, but the battery meter was still indicating that some capacity was remaining. And obviously that's a big problem. So why is that? Well, it comes from the way the system calculates state of charge. You cannot really measure state of charge. State of charge is something that's inferred. So you need to find a proxy to tell you what the state of charge is. And the way it usually works is you have hard-coded into your battery management system open circuit voltage versus state of charge curve. And that's, for example, that Fick curve here. And when the system wants to know the state of charge, it waits until the battery is rested, so at its thermodynamic potential, and then it reports the voltage of the pack on that OCV curve, and that gives you the state of charge. So for example, in a 3S string, measuring 11.5 volt corresponds to a 25% state of charge. And it does that throughout the life of the battery. The problem is, as I just showed you, the voltage response of the cell changed with aging. And that means that that OCV curve evolved with aging. So in that example, in that battery pack, that's the change here from that full curve to that dash curve show you how the OCV change with aging. And the implication of that is that towards the end of life, those 11.5 volt only corresponds to 10% state of charge. So if you don't update that OCV curve in your BMS, you can go into the situation where you think you have 25% capacity, whereas you only have 10%. And that's how you can be stranded on the road with a battery meter telling you, but wait a minute, you still have some capacity. The difficulty is to be able to update that curve. Because again, path dependence of the degradation, every battery degradation is going to be different. And so for every vehicle out there, at every point in time, the OCV curve is different. So you need to find ways to update that OCV curve on board based on some information you can gather at the vehicle level. And so you can try to be accurate. So that's where a lot of work is still needed. And a lot of people are working on that. And in recent years, I'm sure as you're well aware of, there's been a lot of push towards using machine learning to try to solve this issue. Because that would make a lot of sense. The algorithm could look at the onboard battery data and use that knowledge to try to predict how the OCV curve change. The problem I see in the effort right now is that although there's a lot of effort on the algorithm development, which is great, and some of the results are truly amazing, there's little to no effort on the experimental part. And that's a bit troubling. Remember the path dependence. You want to make sure that you test and validate your machine learning algorithm on a wide array of scenarios, because in the field, pretty much anything can happen. So you want to make sure that your algorithm are going to work on path A, path B, path C, path D. And from what we've seen in the literature so far, the best study we could find was 124 batteries, but they only varied the charge. And it's a great study, but they only varied the charge. And their discharge was constant current. So it was not even corresponding to a particular application. So we cannot really extrapolate their results for electric vehicle applications or for grid storage application. That's a great study, but the applicability is limited because they did not consider the path dependence of the degradation. So we need to go towards more big data. We need to be able to test all the machine learning algorithm on a wide array of data representative of all the possible degradation. And a solution to ease that, because experimental data is really costly, time-consuming, and require a lot of know-how, is to use transfer learning and using some synthetic training data to complement the experimental data to train the machine learning algorithm. And so to create synthetic training datasets. For us, we chose to use the mechanistic approach I showed you in the first part of this talk, because it's really simple and it's really fast and it does not require a lot of calculation. And so what we can do is, if you take the example of 1 year of testing, once we diagnose it, we know of the loss of lithium evolved, of the loss of positive evolved, of the loss of negative evolved. And in that case, where all three were linear, we can use those equations to recalculate the voltage curve. And so we have two sets of data that are virtually undistinguishable. One took 1 year of testing, one took less than 0.1 second to calculate. Actually, it's more with R2 is more 0.01 second to calculate. And of course, why stop at that particular condition? Now we can change the mix of those three degradation to simulate every possible degradation. And that's what you see here in the ternary diagram. If you consider a triplet of those three parameters, you can plot every combination of those three of them on that plot. And it's not a red triangle. There's a lot of little red dots here. That's every combinations of loss of negative, loss of positive, loss of lithium we tested. And for each of those combinations of degradation, you can look at different extent of the degradation. So your degradation could be 30% loss of lithium, 50% loss of positive, 20% loss of negative, and have 20% of loss of positive, if that makes sense. And so you add another dimension to that triangle. And every point in there is a unique voltage response of the cell for a unique degradation path and a unique degradation extent. And that means that we created a data set with an infinite amount of voltage curve that you can try to validate diagnosis algorithms, because there are all the possible voltage curves. Yeah, if you're interested, we published it earlier last year, so you have a reference here. Now, for duty cycles, you can use the same approach, and you can use any equation you want to simulate the evolution of the loss of lithium, loss of positive, loss of negative. And then once you simulate the evolution you want, you can use the model to, for that particular combination of loss of lithium, loss of positive, loss of negative, that's where I'm at on that 3D triangle. And so you can visualize the degradation path on that curve. And so you can harvest those voltage curve and the capacity to create the data set corresponding to that particular evolution of the diagnosis. And so if you're interested in that, we have a paper here where you have one data set that's available for download for free. And we just published, I forgot to put the reference in there, but we just published in the journal Energies a new publication on that with 5 times more resolution of the voltage curve and data for LFP, NCA, and NMC 811. So if you're interested, all that data is available to download. So you can try any algorithm you want on that data set. Miriam asked me to show you how you can predict the impact of chemistry usage on calendar aging. And my answer is, right now, we cannot really predict that. What we can predict is under a given degradation, how the voltage is going to change. But we don't really know a way yet to predict how the cell is going to change under some different conditions. And again, that's because of the path dependence. And here, just to show you some examples, that's a paper we published in 2018 on calendar aging, where we surveyed the literature for all the calendar aging studies to see the impact of temperature and state of charge on the different chemistries. And as you can see, depending on the chemistry in your battery, the degradation is completely different. So even calendar aging is going to be dependent on your chemistry, the temperature, state of charge, and so on. Another way you can see that data, and that's a great plot developed by Philippe Deschamps in Aachen, and you have a website here, where we try to find a new way to plot a huge amount of data to try to make sense and try to see trends. And here you have a plot for calendar aging and cycle aging with different colors representing different studies and different chemistries. My point here is there's not really any trend. It's really complex, and with the tools we have now, impossible to predict beforehand, or for that particular chemistry, if I use a battery in that way, that's how the cell can degrade. So we still need a lot of work to understand that. Okay, I want to use just a few minutes I have left to talk a little bit more about our work and how we applied those methods to real data and real systems. So first, looking at grid-tie storage, we've been really lucky in HNEI to be involved in a project with ONR, where we installed 3 large-scale battery energy storage systems on the grid. There is one on the northern end of the Big Island that have been in use since 2012. And we have one on the main island of Oahu here, to give you inside Honolulu is around here. And we have one on the island of Molokai, and they're all 1 megawatt or more. And in addition to having those systems on the grid that we monitor 24/7, we also got the exact same cells for me to test in the lab. And so what we did is we defined some experimental protocol where we, from the field data, we analyzed the usage, and that was to understand how the cells were used in the field. Remember the path dependence. We want to make sure that in the lab, we test the cells in the same way they are used in the field, so that our results can be compared. So we use that knowledge to design an experiment, and then we're going to analyze the results of the experimental part and the field data using the same tools. So we can see if we can match the degradation, and also if we can use that to forecast the durability of the BSS on the grid. And so most of that work is published already, but we've analyzed 3 years of usage to try to get a snapshot of the usage of the cell. And we defined 5 parameters to quantify the usage. We had the current for each pulse, the current, the duration, the temperature, and also kind of a larger time scale, the SOC swings and the SOC ramp rate. And from there, we define an average usage and also some minima and maxima. And we use that information to define a laboratory experiment where we varied the temperature, the rate, and the SOC swings. And we tested those cells for more than a year in the laboratory. And you can see here the results of the degradation. The larger the circles, the more capacity was lost by the cells. So you can see the impact of the different parameters. Overall, the capacity increased with temperature and current and decreased with change of state of charge. Then we can use that knowledge to forecast the capacity loss. The laboratory test was about up to that point here. Now we can extrapolate based on our tools, based on the quantification of the loss of lithium, loss of positive, loss of negative. And we can forecast that under some conditions, we might see an acceleration. The good thing is so far, the BSS is not under conditions where we forecast an acceleration before 15 years or more. So we've been monitoring the BSS system using that knowledge to try to pinpoint if the degradation is going to accelerate or not. If you're interested, everything is published. So if you need the paper, please let me know. Now, the other thing we did, and that's maybe from what Miriam told me, the one you're more interested in, is Vehicletogrid. We wanted to understand the impact of a Vehicletogrid usage on the degradation of the battery. And so we kind of followed the same approach. We first define an experiment where, based on where you most likely to want to participate in Vehicletogrid, try to test different combinations. So what we did is we simulated some driving first. Again, path dependent. We want to make sure that we use the battery as close as possible as the real usage. So what we did is we have a database of electric vehicle data. So we took one commute. So that's a real drive into work for one of those users, and that's a real drive back home for the same user. So it's not the same usage going to work and going home. And then while at work, you could either do vehicle to grid. In that case, it was energy arbitrage, so constant power for 1 hour, or you can do nothing, or you can charge and rest and save things at home. We also did a calendar aging experiment, because obviously the big difference between charging for grid to vehicle or delayed charging, the big difference is at what state of charge the cell is staying the most. If you charge right away when you arrive at work, your cell is going to spend most of the time idle at high state of charge. If you delay your charge and only charge right before you leave work, your cell is going to spend most of its time at a lower state of charge. So it's important to test calendar aging as well. And what we found is for that scenario, meaning constant power at around to give 25% of the battery capacity to the grid twice a day, that was really detrimental for the battery. But we also found a big impact of calendar aging for those cells. And that's actually really significant. If you take the example of 45 degrees at 70% state of charge, the capacity loss is around 20% in 5 years forecasted. And so for an EV battery, 20% capacity loss is usually when the battery is considered done and it's retired. And so that means that for those cells, just from calendar aging alone, just leaving your electric vehicle almost fully charged, parked for 5 years at 45 degrees, is going to kill completely your battery. And so what we showed is that on its own, Vehicletogrid is not worth it. But if you combine it with calendar aging and use Vehicletogrid to go to lower state of charge, then it can be beneficial for both parties, both the utility, because you participate in Vehicletogrid, and both for the EV owner, because you extend the life of the battery. Going back, and I promised that the last time on the path dependence, we obviously also wanted to test the same batteries under a different usage. And so what we did is another study where we still drive the cells, but then we did Vehicletogrid using only frequency regulation. And we did that during the charge or during the rest at different level. And in that case, the good thing we did, because we found that for that particular cell, that particular usage, frequency regulation, is less damageful for the cell than the constant power we did before. Although we did a little bit less. Here we did 15% additional capacity at most. The other study was 25%. But overall, that seems to be less aggressive. So that shows that you want to make sure you test your cell under representative condition and that you test different usage, because some cells might be really good for one and bad for others. And with that, I want to conclude. So I hope I showed you our battery activity at HNEI. We do everything from field testing to laboratory testing and to modeling to develop a lot of tools to ensure reliable and safe battery operation. And we have many collaborations all over the world, and we'd be really happy to start new ones if you guys want to collaborate. And with that, I really want to thank all my students all over the years, especially Arnaud Devy and Cyril Truchot, and my current funding from ONR, SAFT, and Element Energy. With that, mahalo, that's thank you in Hawaiian for your attention, and I'll be happy to take any questions you may have.
Thank you so much, Matthieu. You shared so much information, and I think it's excellent that you made an online tool available and also datasets available. We will link to the online tool under the YouTube video. There are some questions in the chat, and
Okay.
Actually, I had a question, and maybe you touched on it, but I was reading the questions of the chat, so in the last bit, but I will ask it anyway.
Sure.
Easy to separate the impact of driving and grid services and aging?
I wouldn't say it's easy, but if you make the correct if you have a good experimental design. That's a thing we implemented a lot in recent years, and that's, I haven't seen much in the literature, a little bit more lately. If you use design of experiment, it's statistical tools so that you can define an experiment to make sure you can extract the most knowledge and make sure at the end of experiment, you can extract the impact of each component individually and separate the contribution from one factor to the other. So we usually spend a lot of time defining our experiment so that we can make sure at the end we can reach the conclusions we want to reach. So once the experiment is defined, yes, it's pretty easy to separate the contribution. It's just the different diagnosis, and then you see the difference. A lot of work goes into the actual setup of the experiment.
And then in the real world?
Well, the real world, it's you will need some maintenance cycles. I mean, with those techniques, you still need the car to be, if you want to use that diagnosis method, you need to be able to have some constant current charge or discharge, and if possible at low rate. So you will need to bring the car, and for example, during charge, record the charge at a level 1 or something slow, and then analyze that charge to diagnose it. And that's actually doable. But for those methods, you need some constant current charge or discharge. I mean, obviously, for an EV, the constant current charge is much easier to get and as slow as possible. Then you can look at the derivative curve and you can diagnose the loss of lithium and loss positive, loss of negative. And from there, you can see the impact.
Okay, thank you. And from that answer and from what you shared a bit during the last bit of your presentation, I believe we answered one of the questions about, is using EV for V2G and driving more likely to degrade the battery than just using the EV for driving?
Yes, it is, but it could be beneficial because the degradation is different. Calendar aging usually induces a lot of some loss of lithium. And that's a bad thing, but that's also a good thing because that loss of lithium kind of protects you against lithium plating in a weird way. And if I had time, I could explain it. But you can actually, by degrading your cell a little bit, by adding more loss of lithium, you might extend the life of a battery overall because you prevent that accelerated degradation to happen. So there are some sweet spot where it could be, even though you degrade the cell a little bit more, it could be beneficial. There is I wrote a paper on that in collaboration with people in Warwick on that, or you can, actually you need to look at both the calendar aging and the cycle aging to actually see the real impact of Vehicletogrid.
In terms of cycling degradation, does a full cycle have the same effect of 10 small cycles?
That's going to depend on your chemistry. That's going to depend on the change of phase. For example, if you have a material that has a really big structural change at high state of charge, doing small discharge or full one is not going to change much. You're still going to do that big change of structure, and over that's going to degrade your battery. And also, you could see at the loss of lithium, calendar aging happen at high voltage, more at high voltage and high state of charge. So by doing full discharge, you spend less time at high voltage and high state of charge. So you're going to see less calendar aging. So it's a really complex question. I don't have any definitive answer to that. It's really going to depend on the chemistry, on the usage itself, on the temperature, on many factors.
Okay. We also have a question about, to give some context, so the utilization patterns will not always be 0 to 100% state of charge and back. And also, Rido is talking about, to have the validation measurements, we would fully charge and discharge the battery to measure the capacity, but that would not be done regularly. So based on this, will we have partial pass in the voltage versus capacity curve? In this case, how precise would the diagnosis and prognosis methods will be? And the question is in the chat box if you wanted to have a look.
Yeah, no, That's a really good question. And again, that's going to really depend on the chemistry. I mean, if you have some chemistries with all the peaks on the derivative curve, if you have peaks everywhere, then partial charge or partial discharge could work. If we have enough sensors, in a way, to me, I see each of those peaks as a feature of interest or kind of a virtual sensor to diagnose the cell. If we have enough of those sensors, we can diagnose. We don't need to have a full charge. But again, it's going to depend on the chemistry. For some chemistries, we need the low voltage information because there's not enough sensors to diagnose the cell fully with what we have at high voltage. So it's a really interesting question. And again, I'm sorry, I always give the same answer. It's really going to depend on the chemistry. But the good thing is with those tools and the synthetic data set, you can try. Nothing prevents you to take one of my data set and or data from other people, of course, but validate your diagnostic method on full charge or half charge or partial middle. That's, I think, to me, the most important message is saying the technique we developed are the best. I'm not saying that. I'm saying that we give you the synthetic training data set, go wide with it, try all your method on them, and you might see that where your method work best, when they might be improved, where you need the full charge, where you can go with only a partial one, and try on different chemistries. I think that's, to me, where those synthetic data sets can play a big role, is to help people validate on a much larger data sets.
Thank you. How precise is the state of charge estimate in battery packs as the one you presented? Is it 1-2% or more?
You mean current or with the, I mean, if you upgrade the OCV curve properly, and if you upgrade the capacity ration properly, meaning the relationship between capacity and state of charge, most of the time you recalibrate the state of charge using the REST method I showed you. And then you have some dynamic algorithm that's going to track how much capacity you charge or discharge since that reference point and convert that to state of charge. If both of those numbers are updated and up to date, the accuracy, 1 to 2% is not a problem. Obviously, it's going to depend on a few factors, like if you have a big voltage plateau, obviously you're not going to be less accurate than if the voltage is varying a lot. But if you don't upgrade the state of charge curve, the OCV curve, then the accuracy is going to be far lower than that. 5, 10, 15% is likely.
Matthieu added that if you get a reading of 50%, how sure are you that this is 50% and not 48 or 52%?
Well, again, it's really going to depend on the chemistry. If you have, let's say, LFP batteries where the voltage response is really flat, let me show you. If your open circuit voltage is in an area like that, when the voltage is really sloppy, if you say 50%, that's 50%, because there's a big difference between plus 2% and minus 2% in terms of voltage. But if you have a chemistry more like that, where the voltage is a plateau, then if you're on a plateau here, plus or minus 2% correspond to really little voltage variation. So you're going to be less accurate on lithium iron phosphate where you have a lot of plateaus than for more lithium cobalt oxide type battery where you have, where is my curve? I forgot. Where you have more sloppy response. Does that make sense? Here, you're going to be more accurate on if your OCV curve is something like that, you're going to be more accurate than for LFP battery where you have a lot of plateaus.
Yeah, so Matthieu is saying yes, thanks. So I noticed that we're out of time, but there are a couple of more questions. Are you okay to stay for another 5 minutes?
Yes, absolutely.
Thank you. So why OCV curve change with aging?
Because of the path dependence of the degradation, because of the change of matching of the positive and the negative because of degradation.
Okay.
So if the matching of your positive and negative change, your OCV change.
Okay, thank you. Does the size of the battery matters. So we started with 24 kilowatt hours battery. Now it's more 40 and 60 kilowatt hour batteries, considering these batteries are more likely to do grid services or maybe even bigger batteries. Do you foresee that the impact on bigger batteries is going to be less than on smaller batteries?
No, I mean, if your batteries are homogeneous and you don't have any temperature gradient and if the contacts are all the same and so on, it should be the same. The problem with larger batteries is usually they're made in smaller numbers, and so you have a bit more variations between them. But the benefit is usually you have less batteries in your pack, so you have less contacts to take care. Homogeneity in battery packs is a big issue, and there's still a lot of work to be done to understand it fully and understand its impact on performance. That's still something we're working on, but it's really hard for us at the lab scale to do it because we don't have access to much large battery packs. That's something we'd be really interested in doing, but we need some partners that are willing to share real data from large battery packs. In my lab, I cannot test 10 large battery packs with different configurations. I cannot do that. I don't think.
We're talking electric vehicle large, not grid connected large.
Well, even electric vehicle large. I mean, those packs are for the lab scale, at least for my lab. I cannot even test one of them properly, meaning charging and discharging it controllably, getting the data from all the cells. That's a lot of power. And obviously, if you want to understand the impact of cell-to-cell variations, you need to repeat the test on several packs and doing exactly the same thing on several packs. So that's a lot of work, and that's a bit above what a normal lab can do. I mean, maybe places like the National Lab in the US can do it. Maybe in the UK, places like Warwick, I'm fairly sure they can probably do it. But yeah, I don't think people have really looked at it as deep as we need to quite yet. But that would be really interesting to start to quantify that. In a way, it's a bit, we have a French saying that says appetite comes with eating. And I think that's true in a way that now those methods work so well at the single cell level. And we've been developing them for 10 to 15 years now. But now we're slowly moving towards the pack. But 5 years ago, we could not do packs because we didn't understood the single cell well enough quite yet. So we are getting there. I think that's a natural progression now that not that we're getting bored with single cells, but for the single cells, we have the automated fitting tools. It's working well, it's validated. It's less exciting. And I think the battery packs, applying those methods to battery packs is probably one of the next big things with machine learning.
Yeah, it's definitely a couple of exciting decades to come. And considering that last decade, plenty has been done. Last couple of ones, do you expect, or has there been a lot of examples where there was a sudden loss and the car stopped because the battery died?
I don't know. And I'm not sure that's something they like to publish on. I just found that one example, and it dates a little bit now, but I really like it because it's proving my point really, really well. I'm not aware of any other example. But if anyone has other example and it's like you have an article or something, please send it to me. I would love to update my slide and have some more vehicle than just a Tesla, because I obviously don't want to imply that only Tesla does that. I'm pretty sure all of them do.
You did put Tesla in a couple of your slides, so I wanted, anyway, I'll ask it anyway. Do you think there is something related to battery degradation that Tesla did not go to V2G yet?
Well, all I showed you, I mean, the study we did was on a Panasonic cell that believed to be quite similar to the one the Tesla Model S. You see, I'm taking precautions here. I'm not sure it's exactly the same cells. According to many people, it's the same cells. That cells seem not to like too much some Vehicletogrid. I think it's mostly a matter of warranty. I think the EV owners are giving you 8 years of warranty or something like that. depending on the vehicle and depending on what country you're in. If you start doing vehicle-to-grid, your battery is going to degrade really, really fast. And so they don't want to have to pay for a new battery every 2 years or so.
Have you different batteries in cars? And
say that again.
And I wanted to check if you're aware, like right now, since this is the new technology, do you think all types of batteries in different cars are similar, or would you think there are better batteries in certain cars without naming?
They're all different. That's for sure. Some are slightly different, some are really different, but a lot of EVs in China are using iron phosphate. I'm not aware of any iron phosphate cars in Europe. I mean, there was the blue solution car in Paris, but those were solid state iron phosphate cars, so even different than the graphite iron phosphate that China has. They're all different. Which one is best is going to depend where. I'm pretty sure each of those vehicles would thrive under some conditions and be really bad under others. I mean, some's going to do great in mountain roads, some's going to suck at it. And the opposite might be true in a really dense city. So to me, more work is needed to adapt batteries to where you want to use it. I don't think a car can have one battery to fit driving in Switzerland, UK, Hawaii, or whatever. We should have batteries adapted to the environment. That's my understanding.
Great, thank you. There's one last big question. Are you up for it?
Yes.
Okay, so do you have examples of using this mechanistic approach to analyzing degradation to changes in manufacturing, example processes, cathode composition, to result in new batteries with less degradation?
We do to some degree. We did in a couple of years ago, studied 100 cells and fitted 100 cells to see the change in loading ratio and offset induced by cell-to-cell variations. So that could answer part of your question. So there are small thermodynamic variations there. We studied a lot cell-to-cell variations using the mechanistic approach or some normal ones. So a lot of work has been done by us and others on when you have cells, first try to characterize the cell-to-cell variations. And that's something we always do. When we start a new study, we always buy as much cells as we can, 100 or more, and we test them all first to understand the cell-to-cell variations before we actually start the experiment. Then for cathode composition, that's a bit more complex. I mean, a lot of people have been using those derivative incremental capacity at the half cell level for decades. And that's much easier because you don't have that convolution with graphite. So yes, I mean, there's plenty of examples out there of people using those derivative curves to study the impact of composition. Not our work because we don't develop materials, but those techniques have been around since the 60s for half cell. For full cell, it's mid-2000s.
Great. Well, thank you, Matthieu, and thank you for the participants for this discussion. Where can they find you if they have more questions and want to get in touch? And would you like to add anything before we end?
You have my email on the last slide, probably.
Oh, yes.
Yes, you have my email here. So yeah, please, if you have questions, send me an email. And no, I have nothing to add. Thanks for having me. And yeah, no, I mean, I guess my message would be consider the material science behind it. When you start to develop algorithms, think that batteries are really complex system, and that understanding the material behind it is going to help you build much better diagnosis and prognosis tools. The black box approach not going to lead anywhere.
Great. Thank you so much, Matthieu. Goodbye.
You're welcome. Bye-bye.